In this question, we have a steel alloy again and a circular cross-section with a diameter of 10.70 millimeters. The mechanical properties given: yield strength, UTS, and Poisson's ratio, also Young's modulus or elastic modulus. The question is in three parts. The first part asks, if a tensile force is applied, determine the change in diameter. So if we again draw our uniaxial tension setup with our coordinates, Poisson's ratio is defined as negative of strain in x direction or lateral strain to longitudinal strain, and this is going to be delta D over D0 over delta L over L0. This is the length and this is the diameter. Okay, the tensile force is given as 16,256 newtons. We have the yield strength as 300 megapascals, the UTS as 500 megapascals, Poisson's ratio as 0.33, Young's modulus as 229 gigapascals, and we also have the original diameter as 10.17 millimeters. Now we need to first find the strain in the y direction. So Poisson's ratio is minus epsilon x over epsilon y. First we calculate the epsilon x. First we calculate the epsilon y. The epsilon y has to be calculated from Hooke's law. So we need to check whether the material has exceeded the yield strength or not. So the stress is going to be P over A0. P is given as 16,256 newtons. A0 has to be calculated. We know the diameter as 10.17 millimeters. So if you calculate this value, this is going to be around 200 megapascals. So our applied stress is below yield strength. That means Hooke's law is valid. If Hooke's law is valid, then we can write stress is equal to elastic modulus times strain, and this strain is going to be strain in the y direction. 200, convert this to megapascals, times epsilon y. If you do the calculation, epsilon y is 8.739 times 10 to the power minus 4. Now we know this, then we can calculate epsilon x and we can calculate the change in diameter. So epsilon x is going to be Poisson's ratio times epsilon y with a minus sign, minus 0.33 times 8.739 times 10 to the power minus 4. If you calculate this, it's going to be minus 2.884 times 10 to the power minus 4. Then this is equal to delta D over D0. Then delta D is epsilon x times D0 . We have the D0 as 10.17. Then the change in diameter is a reduction of 2.933 times 10 to the power minus 3 millimeters. That is the answer of the first part of the question. In the second part, it is asked that if we increase the load to 38,000 newtons and the strain is measured as 0.03, determine the elastic and plastic strain values. So in this part, the total strain is given, and we need to separate these. So first, for the given load of 38,000 newtons, we calculate the stress. With our simple P over A0 expression, and A0 is the area of a circle. This turns out to be 467.8 megapascals. So we are clearly above the yield strength. We have plastic deformation in the material. And if we draw a hypothetical strain curve for this material, so this is around 500 given in the problem, this is 300, and we are somewhere here. And this is the total strain. So again, if you unload, it's going to be parallel to the linear portion with a slope of elastic modulus. And this part is the elastic part of the strain, and this part is the plastic part of the strain. The elastic part is simply applied stress divided by Young's modulus. Again, if we divide and convert Young's modulus to megapascals, we find the elastic part of the strain as 2.043 times 10 to the power minus 3. Then we have this, we have the total strain, 0.03, elastic plus plastic, then plastic is total minus elastic. Then this turns out to be 0.027957. And if you convert this to, again, percentages, (93.2% of the strain is plastic, and 6.8% of the strain is elastic. In the last part of the question, it is asked, is this material suitable for a spring application with a required resilience of 400 kilojoules per meter cube? So first, let's talk about what resilience is. Resilience is the elastic energy absorbed, which means the energy absorbed by the material until the yield strength is seen. Let's say this is the strain at yielding. So if we assume this part is linear, then the resilience geometrically is the area under the stress strain curve, and this can be calculated as such, area of a triangle. And from Hooke's law, we know that sigma y is going to be equal to epsilon Young's modulus times epsilon y, and epsilon y then is this. So if you substitute epsilon y in here, then you get UR as square of yield strength divided by 2 times the elastic modulus. Then we can directly substitute the values given in the problem. 300 megapascals divided by 2 times 229 times 10 to the power 3 megapascals. If you calculate this value, this is 0.1965 megapascals. Okay, so the unit given to us was kilojoules per meter cube. Now, Pascal has the units of newtons per meter square. If you multiply both sides with meters, then you get Newton meter per meter cube, and Newton meter is joules. Then we have joules per meter cube. Now 1 megapascal is 10 to the power 6 pascals, which is 10 to the power 3 joules per meter cube. The question gives us 400 kilojoules per meter cube. Sorry, this is 10 to the power minus 10 to the power 6 joules per meter cube. If you convert this to kilojoules, then you simply divide by 1000. So 1 megapascal is 10 to the power 3 kilojoules per meter cube. Then this value is simply 196.5 kilojoules per meter cube. The required value was 400, which is larger than our resilience value of 200. So this material is not suitable for this spring application.